Okay, so in class we were talking about the Equipartition Theorem, which tells us that for every degree of freedom, the average kinetic energy is a half kT, and that tells us that the thermal energy should be the number of degrees of freedom over 2 times n kT. And we worked a little bit on thinking about what is this number, right? What is the number of degrees of freedom? And we came up with the fact that there will be translational kinetic energy terms, and so there's usually 3 degrees of freedom from that, motion in all 3 directions. There can be rotational degrees of freedom, and that can take on values 1, 0, 2, or 3, depending, right? So monotonic, atom, single atom would have no degrees of freedom from rotation due to sort of quantum mechanics. A diatomic has 2, and then a general polyatomic atom would have full 3 rotational degrees of freedom around all 3 axes. And then we talked about vibrational degrees of freedom, and there are 2 degrees of freedom per vibrational mode. Sorry, I guess that's 2 per vibrational mode. All right, and we talked a little bit about also that because of quantum mechanics, the energy of the vibrations, and actually it's also true for rotations for that matter, the energy of both rotations and vibrations are quantized. And that's due to quantum mechanics. What does that mean? That means that there's a minimum energy required to excite the vibrational or the rotational mode. So you need to have a certain minimum amount of energy in order to make that vibrational mode start to happen. So there's a so that's telling us that there's a E min, some value of the vibrational mode, right? And so you have to have at least that much energy. Now, where's the energy coming from? The whole equipartition theorem is saying this energy is coming from thermal energy, from the temperature of the environment. So if there's a minimum energy that you need to have to make this mode start to vibrate, that also means that there's a minimum temperature required to make that mode start to vibrate. Right? And the connection is that the thermal energy of that temperature has to be equal to this minimum energy, right? And so kT, this is the thermal energy, right? And so that has to be equal to the energy, say, of the vibrational mode, right? So we need to have enough energy in the environment, thermal energy in the environment, in order to match that quantized energy of the vibration. So, for example, we can do one of these examples on this handout that I gave in class on Wednesday. So, example C here, it says, suppose the lowest energy of the vibrational mode of a particular diatomic molecule has an energy of this value. At what temperature does this mode become active? All right. So what we're thinking about there is it's a diatomic molecule, so this sort of schematically it looks like this, 2 atoms connected by a spring, and so the vibration we're talking about is the 2 atoms vibrating back and forth like this, right? And it's telling us that this has a minimum energy. So this is example C. And I like to sort of think about this, sort of drawing a little picture like this. So this is an energy diagram, and this is 0. And this particular molecule has some value of the vibrational mode. So the lowest energy vibrational mode has a certain value. And so according to the problem, actually I'm going to change this. because that value I wrote wasn't quite right. So the problem says 10 to the minus 19, but let's use 5 times 10 to the minus 21 joules. Pretty small value. Make it even smaller. And so this is sort of what we mean that when we say the vibrational mode is quantized. It can't just take any energy. The energy in order for this molecule to vibrate, the lowest energy it can vibrate in is exactly this value right here. And then there are actually some higher energy vibrational modes, and so in general it'll have a series of quantized modes up there. But you know, they're all going to get accessed as thermal energy matches them as well. And so I sort of think of it like this, that we need to have a certain amount of thermal energy, so this molecule sitting here not vibrating could pick up some kinetic energy from banging into other molecules, and it could get an energy of kT, and that would excite this vibration. So by banging into other molecules, if the other molecules had some kinetic energy of kT, that collision would be enough to start this spring starting to vibrate, and it would move the molecule up into this lowest vibration mode, right? And so the requirement is we just need to have the kT energy equal to, well, that's what we wrote up there, equal to the energy of the mode, right? And so if we're looking for what temperature this will happen at, we just take the energy of the mode and divide by K. So in this particular example, we have 5 times 10 to the minus 21 joules, and K has the value 1.38 times 10 to the minus 23 joules per Kelvin. And so that gets us a temperature of 362 Kelvin. All right. So what does that mean? What's that telling us? Right. So that means that for temperatures here, so for temperatures less than 362 Kelvin, then this vibrational mode is not excited. Right? And so what does that mean? How many degrees of freedom would this molecule have? So this was a diatomic molecule. So it's got 3 translational degrees of freedom, and it's got 2 rotational degrees of freedom for 5 total, right? So that's the number of degrees of freedom for this molecule will be 5 for temperatures less than this critical value that you need to turn on that vibration. And on the other hand, for temperatures greater than 362 Kelvin, now this vibrational mode is activated. And so now the degrees of freedom equals the 3 translational, the 2 rotational, and now we get how many? 2 more for this 1 vibrational mode, right? 2 degrees of freedom per vibrational mode. So that is 7. So the degrees of freedom would be larger now at the higher temperature. And again, some of the terminology, so we would say that for temperatures below 362 degrees, the vibrational modes in this molecule are frozen out, and they don't contribute. And in particular, they don't contribute to the thermal energy, right? So the thermal energy is given by the degrees of freedom divided by 2 nkt, right? And so for temperatures less than 362, the thermal energy is 5/2 nkt, and for temperatures larger than 362 Kelvin, the thermal energy is 7/2 nkt. So a big difference, right? A observable difference in the system. In fact, one way we could sort of illustrate that is to make a little plot of the thermal energy as a function of temperature. And so if we've got this value, 362 Kelvin, so we're saying that the energy is going to have a value of 5/2 nkt until it gets around this temperature, and then it's going to rise up to a larger value, 7/2. So the energy of the thermal energy of the system is actually going to change. And in fact, In fact, this curve is probably going to continue to go up because more and more of these modes, so I mentioned that this is the lowest vibrational mode, but there are other higher energy vibrational modes. So as the temperature goes up, more and more of these modes will be accessed, and so the numbers of degrees of freedom is going to increase, and so the thermal energy of the system will increase, something like that. And I notice that I didn't. It doesn't just go immediately from 5/2 to 7/2. It's going to have some kind of smooth curve that connects those two. As the temperature is increased, there will be a few molecules that have a little extra energy than other molecules do, and so a few of those might be able to start making this vibration go, and that will increase the thermal energy. And then as the temperature goes up and up and up, more and more and more and more molecules are able to get that vibrational mode going. All right. Now, another interesting thing is how could we measure or detect even these vibrational modes in atoms? And so one way that we can experimentally measure the vibrational modes is of an atom or a molecule is to shine light on them. And if the energy of the photons exactly matches the vibrational energy of the atom, then the atom will absorb that photon and it'll start doing its vibration. So sort of schematically what I think of is you have a diatomic molecule sitting here with this spring connecting it, and suppose you shine some light on it. Right, so you shine a photon of light on it, and it's possible. So again, I'm going to sort of think about this in this energy diagram way. So here's E equals 0, and suppose there's some vibrational mode which has a quantized energy, it's a specific energy value. Then if the photon energy exactly equals this energy, so this energy difference between the ground state and the excited state of the molecule, if the energy of the photon is exactly equal to this, then the molecule will absorb that photon and start to vibrate, so move from not vibrating to vibrating. And so the picture would sort of be, it'll absorb it, and so now this molecule will be sort of vibrating. I don't know how to show this thing as vibrating. It's going back and forth. Right? And there's no more photon, right? Because the photon got absorbed by the molecule. Energy went into it. And the cool thing about the fact that these energy values are discrete, so remember, this is this vibrational mode, and there might be another vibrational mode up here which has its own energy. So if the photon has to have exactly the energy of the vibration in order to be absorbed. If the photon has an energy that's a little bit bigger than that, it actually doesn't get absorbed. So how would you do this as an experiment? You could make a sample of your molecule, so a little volume with the gas in it, and you can shine light of a particular wavelength in, and then actually if you could scan that wavelength, so if you can change the wavelength of the light that you're sending in and scan it through, when the wavelength is just the right value to have an energy that matches one of the vibrational modes, the gas will absorb a bunch of light. And when the light doesn't match the energy level, then it'll just pass through the gas. So you can imagine something sort of like this, a little container with your molecules in it, and some sort of laser shining light, so photons of light, through here, and then having them pass through, and having a detector over here, which detects the light. And so then you would get a graph, you would make a graph of the intensity of the light that you detect here, right, as a function of the wavelength of the light. And that might look something like this. So you'll get a lot of light through, you get a lot of light through, until the wavelength of the light matches the vibrational energy of the molecule, and then it'll absorb a bunch of that light. And then as you increase the wavelength again, it'll stop absorbing it. And then maybe you'll hit another vibrational mode, and maybe another, and so forth. So you see some sort of graph sort of like this, where the light passing through your gas is being decreased, so it's being absorbed, when the wavelength of the light matches the vibrational energy of these particular modes. So forth. Right? So what's the condition for that? You have to have the energy of the photon, which is equal to h nu, h times the frequency, or rather hc over the wavelength. Two different ways to write the energy of the photon. So we'll do the wavelength, right? And what you need to have happen is you need to have the energy of the photon be equal to the energy of the vibrational mode, right? And so that's how you can correlate or make a correspondence between the wavelength, where you, say, experimentally measure these things happening, and what the energy of that vibrational mode is. So, for example, if you measure the vibrational wavelength, you would have that the energy of that corresponding vibrational mode is hc over the wavelength of that measured vibration. And so that we can use that to solve problems like this. So the second problem example we had in that handout was this one. So it says the lowest energy vibrational mode of a particular polyatomic molecule is excited by photons with a wavelength of 1.5 micrometers. So below what temperature is this mode frozen out? How many degrees of freedom does the molecule have? All right, so it's just like the question C, except instead of telling us what the energy is straight up in joules, it's indicating to us what the vibrational energy is by telling us what wavelength photon matches that energy. Right, so you can probably see how to solve this. What we do, so this is example D, right, and so what we know is that the wavelength is 1.5 micrometers, right, and so that means that the vibrational mode energy is hc over wavelength. And so if you look these numbers up, they're conveniently in the front of the book, the front cover. So h is 6.62 times 10 to the minus 34 joule seconds. C, you might remember, is 3 times 10 to the 8th meters per second. And then this is 1.5 times 10 to the minus 6 meters. And that works out to be 1.325 times 10 to the minus 19 joules. All right. And so if you want to find at what temperature is this vibration excited, right? We want to set our thermal energy, kT, equal to this vibrational energy. Right, so T is the energy of the vibration divided by K. So 1.325 times 10 to the minus 19 divided by 1.38 times 10 to the minus 23 joules per Kelvin. And so that works out to a rather large number, 9,600 Kelvin. Yeah, which is fairly typical, actually. A lot of molecules, especially small molecules, tend to have rather energetic vibrational modes, and so they get excited only at very high temperatures. Right, so what does that tell us? That for temperatures less than 9,600, right, how many degrees of freedom do we have? Well, it's going to be our 3 translational, right? And what was this? Was a check this out here. This was a polyatomic molecule. It's going to go ahead and have the 3 rotations as long as it's not linearly symmetric somehow. So it'll have 3 rotations. But if we're at a temperature below this value we just calculated, none of the vibrational modes will be excited. So its degrees of freedom would be 6. And in that scenario, the energy, right, being F over 2 nkt would be 3 nkt. And of course, if the temperatures were larger than 10,000 Kelvin, then the vibrational mode would start to kick in, and we would add 2 more degrees of freedom to the system. Okay, so I hope that helps to show how to do these kinds of problems where we're calculating the temperatures at which different modes of a system, vibrations, or even rotations, what temperatures they become excited, and how that affects the degrees of freedom. So you've got some homework problems on the next homework, which are very similar to this. As always, let me know if you have any questions.